So we've now developed models and equations to describe the three different modes of heat transfer that we had hypothesized occurred between objects at the beginning of this lecture series. We had modeled and created equations for conduction, that mode of heat transfer that we believed occurred between two solid objects or within a solid object. We also created models and equations for studying convection, the mode of heat transfer that occurs between a solid and a fluid or between two fluids. And finally, we created models and equations for understanding radiation, the mode of heat transfer that occurs between two objects without an intervening medium that has matter. And having developed equations for all three of these modes of heat transfer, it's hopefully clear to you that heat transfer, as I had claimed at the beginning of these lectures, is an invention. So much of the equations that we've constructed are not necessarily based on a physical principle, but are simply based off of approximations and conveniences that allow us to perform calculations that are basically right, but still not going to be perfectly accurate because of the level of leniency that we've taken when it comes to making these approximations. When we were modeling conduction, for example, we created or approximated a linear relationship between the heat fluxes inside of an object and the temperature gradients. And we only did this based off of certain assumptions that include, for example, saying that temperature gradients are not significantly large inside of the objects that we're considering to model with these equations. We created, for example, or approximated a linear dependence between the temperature and thermal energy, or available thermal energy. And we only did this, again, because of convenience, because we assume that thermal energy differences and temperature differences are small in the problems that we're considering, in the problems that we're modeling, and then we just create the simplest possible equation. And we did the exact same thing for convection, where we related temperature differences to heat transfer rates, or pardon me, to heat fluxes using a linear relationship with a proportionality constant. And those proportionality constants, right, all of those proportionality constants contain all of the physics that we didn't cover in these lectures, which is not a lot. I mean, really think about it. We never really spent too much time thinking about the physical processes underlying conduction or convection. And so all of the physics is crammed into those proportionality constants, which can, of course, be a function of anything. In radiation, we actually did get to see a particular approximation that's derived from sophisticated statistical mechanics theory. Not something we derived, of course, but something that we got to see. But we nevertheless observed that we crammed all of the physics that we don't have the ability to understand in radiative systems into proportionality constants, into the emissivity, into the absorptivity, into the reflectivity, and into the transmittivity. All of those constants are constants that contain the physics that we didn't really care about. And the real story of heat transfer from a physics perspective is what those constants are and how they depend on the material properties and the properties of the system. Something we don't really worry about in the context of studying heat transfer, at least from an engineering perspective. And you may ask yourself, why on earth don't we care? Is it just that our equations are that good? And the answer is not really. Even the best empirical correlations that we can find for, say, a Nusselt number or a heat transfer coefficient are only going to be accurate at best, in my professional estimate, to somewhere within 10, 15, maybe even 20%. Okay? And some people might say 25. And so how on earth can we engineers operate using, a set of equations that we believe are going to be wrong and have an error of up to 25%, if not more? Well, the answer to this is because even though we may not necessarily be great theorists from the perspective of understanding heat transfer, we are very good at constructing control systems. And we are very good at understanding how some variables affect other variables. For example, the correlations associated with Nusselt numbers and Reynolds numbers for external flows and Prandtl numbers, those correlations are very complex. They're based on empirical data and they're not precisely accurate. However, the nature of these correlations does tell us relatively universally that if I have, for example, flow past a flat plate, and I increase the ambient background speed of the flow past that flat plate, that I am going to increase the heat transfer that's happening from the plate out into the liquid, or vice versa. And the reason that this is useful is because we can construct control systems where we manipulate those variables and measure the output, the relevant thermal variables of a given system, and then alter the inputs to alter the outputs however we want. To be a bit more concrete about this, consider an HVAC system in a building. For example, let's say that someone programs the HVAC based off of some calculations that they did using advanced heat transfer calculations and some complicated correlations. They figure out that the right speed at which to make the fan that's driving the HVAC system and the flow inside of the HVAC system, that the right speed is some number in order to make sure that the temperature of the rooms inside of the actual building stay at a comfortable 27 degrees Celsius. But maybe they made a calculation wrong. Maybe there's a factor, like more people go inside of the building than they expect, or maybe they just looked up the wrong correlation in the book, or maybe the correlation isn't even that good. So does that mean that everybody's just going to boil to death? Absolutely not. Because we invented a clever little thing called the thermostat that monitors the temperature of a room. And whenever that temperature gets too high or too low, it sends a signal to an automated, switch in the HVAC system that toggles the speed of the fan. And so, for example, if the thermostat reads a temperature that's a little bit too high, above 27 degrees Celsius, then that thermostat will send a signal to the fan, and it'll say, okay, fan, you have to rotate harder because you have to increase the speed, which will increase the heat transfer coefficient associated with heat transfer between the air and the surface of the vents. And then therefore that will increase the heat transfer inside of the room such that the temperature goes back down to 27 degrees Celsius. And that we do that in an automated way such that we're continuously reading the inputs and outputs off of these kinds of machines such that we don't actually need to necessarily know what the equations are. All we need to know is how one thing depends on the other, something that we have been able to observe, at least empirically, in our study of heat transfer. So it actually doesn't matter that we're not great theoreticians. It doesn't matter that we don't understand the physical principles, the fundamental physical principles behind how this heat transfer occurs. All we need to know is a general sense of the dependencies, that increasing one thing decreases the other or increases the other, and to be able to construct machines that can exploit these dependencies to generate feedback loops that eventually make thermal systems reach an equilibrium that we want them to reach. And that is kind of the point of heat transfer, that it relies so much on invention. All of the mathematics that we've created for studying heat transfer is just a very raw, very rudimentary invention. It is based off of very simple principles in mathematics like linearization. But it doesn't matter because it's useful, because they provide us, the equations that we generate provide us with dependencies that we can use to program control systems that therefore make things like HVAC exist, that make things like the ISS exist. And so, to conclude by stating the thing that I stated at the very beginning of these lectures, heat transfer is an invention, and it is perhaps one of the most useful inventions that humankind has ever created. And your job as a person who now knows about heat transfer is to create something useful with this knowledge as well, and to use that knowledge for societal good. And so I hope that you are able to take the knowledge that I've provided to you and build something good, and to build something great, and to build something that will help other people. Because overall, that's always the point of engineering, right? To enhance or create societal good. And so I wish you the best in your future endeavors, whether or not it involve heat transfer or other fields of engineering. And always think about the way that you can use this knowledge to do good, because that's the most important thing that any of us can do.